Okay, hello guys. Today we are still going to talk about structural analysis again. We are going to analyze a simple supported beam with a uniform variated load this time around. So a uniform variated load. As you can see here, we have a load 10 kilonewton, which is variated all along the beam. The span of our simple support beam is 4 meter. Okay, how do we analyze it? Before even start the analysis, don't forget to activate the notification button and subscribe to the channel for more video. Thank you. Okay, so how do we analyze? We start by the free body diagram by removing the support. So when we remove the hinge support, we have the reaction AX, we have the reaction AY, because for a hinge support we have two restrictions. So now when we remove a roller support, we have only one restriction, which give one reaction force is BY. Okay, so that's the free body diagram, and these are the conventional sign, positive conventional sign that we'll be using for the exercise. So next step, we find the external reaction forces. How do we find the external reaction forces? We use what? The static equilibrium equation. So the summation, we start by the summation of forces along the x-axis equal to 0, which implies that AX is equal to 0. As you can see here, we have only one forces along the x direction. So now we go for the next one. The summation of forces along the y direction is equal to 0, which imply what? That will have AY, which is pointing upward. According to the positive sign is positive. You have plus BY also pointing upward. According to the positive sign chosen, we have plus. So we have now negative QL divided by 2. This negative QL divided by 2 represent the resultant of the force exerted by the load on the simple supported beam. The resultant is getting by calculating the area of this load that is exerted on our structure actually. So we calculate the area by doing the height times the length. The length here represents the span of our beam, which is L, and the height represents the load, this load 10 kilonewton that has been given, okay, for the side. So we have that, and since we have it pointing downward, according to the negative the positive conventional sign chosen, it will be negative QL divided by 2, which we'll name it equation 1. So now we go for the third equation. Summation of forces, summation of moment around the A axis equal to 0. So we'll have the moment of the force AX plus the moment of the force AY plus the moment of the force BY plus the moment of the resultant forces exerted by the load QL divided by 2 is equal to 0. And as you can notice, we have the moment of the force AY, the reaction force AY is equal to 0, because as you can see on the diagram of the free body diagram, we have AX, which is meeting the axis of rotation, so the moment is equal to 0. We have AY also meeting the axis of rotation, so the moment is equal to 0. We are left now with the moment of the reaction forces BY and the moment of the resultant forces. So now the reaction of the moment of the reaction force BY is given by plus BY times L. Y plus, we have BY rotating towards, is rotating like this in this direction towards the A axis, which is the positive direction of rotation. So we have plus, then we have the distance from BY to the axis of rotation, which is the span of our beam L. That's why we have BY times L. So that's the moment of the reaction force BY. And now we have the next force, resultant force, which is here, is applied at the center of our gravity of our uniform variated load. Actually, as you can see, I name it J. So this is applied at the center of gravity. To have now the moment of this resultant force, will make the we can see that first of all, for the sign is rotating like this, is going around the A axis, is going to the opposite direction, is going in the opposite direction of the, according to the positive sign convention shows for the side. So that's why we have a negative here. So now we already have the force, which is QL. We have to multiply in times the distance from the axis of rotation, which is 1/3 of the total span of our beam. That's why we have negative QL divided by 2 times 1/3 of L. So we have, by doing this, we have the moment of the resultant force. Now we are coming out with By, which is finally equal to QL divided by 6, which we name equation 2. By doing numerical application, we come out by with By, the reaction force, equal to 20 divided by 3 kilonewton. It's in kilonewton. Okay, so now we take equation 2, which is By, we substitute in equation 1 to have the reaction forces Ay also. So Ay now plus QL on 6, which is By, minus QL on 2 is equal to 0. Will come out with Ay is equal to what? To QL divided by 3. Okay, so doing numerical application, we will see that the Ay is equal to 40 divided by 3 kilonewton. That's the magnitude of the force, of the reaction force. Pardon, excuse me. Now we are done with external reaction force. We go into internal reaction forces. So how do we get the internal reaction forces? By making a curve. Always remember, we make a curve to have the internal reaction forces. So we will consider a curve from B at a distance x from the point B, with x within the interval 0 to 4. So that's our x within the interval 0. This is the section that we made. Okay, this is the axis of rotation here. This is the bending moment, abbreviate BM, and this is the shear force SF. Okay, now our load here will not be more we will not more call it Q, because we are making a section. We will now call it Y, and now this is the distance x well represented. Now the resultant force is exerted by the load on our structure now is called YX divided by 2. Remember, that's how we get the resultant forces in the previous step. So that's now is called now YX divided by 2, which represent the resultant forces after the section. Now we have you can notice that we have substituted the Y by Q, because it's no more a Y now, and we still have the reaction forces By. This is the conventional, the positive conventional sign that we'll be using to have the internal reaction forces. So first of all, the first thing that we'll have to find the expression of Y in this case before continue to get the internal reaction forces. So by using from Thales theorem, we can know it's a triangle. So we can note, we can have Y over X, which will be equal to 10 over 4. 10, remember, was the load given initially. 4 was the span of our structure, the length L. And now we know that as you have made the curve, if you are to represent it here, we'll have something like this. So this was Q, this is now Y, and here you have the total length L, and here now you have our small length. This is our small length X. Okay, so for the Thales theorem, you know that we can write Q divided by L is equal to what? To Y divided by X. So that's how we get the expression of Y, which is equal to what? The expression of Y is equal to 10 over 4 times X. So once we get the expression of Y, we can now find the internal reaction forces. Okay, so summation of forces are in the Y direction, because the shear forces in the Y direction is equal to 0. You have the shear force pointing upward, positive. The reaction force is pointing upward, according to this is positive. And now we have the resultant forces exerted by the load, which is negative, pointing downward. As you can see, it's coming from the center of gravity of this section, so it's pointing downward. So according to this positive conventional sign, it will be negative actually. So we will have as I said, to have the resultant force, we have to calculate the area of this triangle. That's the load applied, the variated load applied on the structure. That's why you have the y times x. Y is the height, length is x, and since it's a triangular shape, you have height times length divided base times height divided by 2. So that's why we see write this. We see what this is equal to 0. So at the end of the day, doing the manipulation, will come out with the shear force, which is equal to what? Yx divided by 2 minus by, with y is equal to 10x over 4. We'll have the shear force equation will be equal to 10x squared. This 10x squared, okay, 10x squared divided by 8 minus 20 over 3 kilo is in kilonewton. That's the expression of the shear force. 10x squared divided by 8 minus 20 divided by 3 in kilonewton, all in kilonewton. So now we have to look for a bending moment. Now to have the bending moment, we apply the summation of moment around the x-axis here, which is equal to 0. So so the shear force now, the shear force, to have the moment of the shear force, we will do the shear force times the distance. Since the distance is 0, since it's meeting the axis of rotation, we will have the shear force that will cancel here. We have B, the reaction By. We will look for the moment exerted by the force reaction By. That's By times x, because as you can see, if it's rotating like this, it's positive, is rotating in the same direction, same positive sign chosen according to this. So you have now B times x. X is the distance from the direction of By and the axis of rotation. Now we will be left with a negative bending moment. According to this, you can see that our bending moment is going in an opposite direction according to this, so it's negative here. And now also we have the resultant, the moment of the resultant, which is the resultant himself, right? Itself, the resultant itself times the distance from the axis of rotation. The resultant is already known, which is yx divided by 2 times now the distance from the axis of rotation, which is x here, to the direction of the resultant, which is 1/3 again, 1/3 of x again. So we are at the end of the day, and here, as you can see, it's negative, because if you are to rotate the resultant like this, is going to the opposite direction around the x-axis. It will be in the opposite direction, it will be rotating in the opposite direction. So after manipulation, you will come out with the expression of the bending moment, which is equal to negative 10x cubed over 24 plus 20x plus 20 over 20x over 3. This in kilonewton meter. Remember, the negative here is just showing you that the positive, the sign the direction of the positive direction sign of the rotation sign that you shoot is just the inverse to have a positive here, so that you will be using that rule to check if this equation is matching with the equation of the shear force. So there is no problem with the negative actually. Okay, now we are going to look, since we have a quadratic equation here, we are going to look for the maximum the maximum bending moment before starting drawing the bending moment diagram and the shear force diagram. So let's look for the maximum bending moment. Okay.